Okay, so welcome back. I just have the local. I'm running the file locally. I've installed that upgrade here. Now that should work. Yes. And let's just quickly look into that function. Just quickly. So here's what it does. Right, I just read in some return panel, or here now it will be the variance. And then it runs a Jacques-Barra test. And it plots the density in terms of the set score. Okay, that's all it does. So let's just do that. Yeah. So the question is the variance Gaussian? Okay, and we just appreciate for the moment what a histogram of realized variance looks like. Yeah, so very clearly visible that right tail, so that positive skew. See that in all of the different underlines. There's some, yeah, but also here, that looks more like a uniform distribution. Yeah, but then here you see long tail. It's the Z-score. So these are 5 standard deviation events. BMW up to 6. Okay, yeah, so you can choose the firm you like. Let's just go down to Volkswagen. Volkswagen. It's interesting. That looks like a uniform. I don't know. It's, yeah. And then the market here. Okay. So let's recap. Variance method 1 has been computed or was computed using the squared return measure. Now, next thing is we visualized it and we want to know what's the variance tomorrow? What's the variance in a day, in 2 days from now, 1 week from now? Now, if we take the squared return as a measure for variance, we cannot state variance forecasts just like that. Because what do you need to make a forecast? Either what you extract is already a forecast, or if you just have today's variance, you need somehow to put that into something that gives you a forecast. That could be a parametric model. It could be that you run regressions, like what I'm suggesting here. Yeah? How to produce forecasts for the variance using return square as the measure. Well, I was just thinking myself, you could fit the time series of squared returns, either using a parametric, non-parametric, linear, non-linear model. That's what you can do. You will always rely on this backward-looking data, these backward-looking regimes, and hope that what is going to come was captured by that backward-looking data. Keep in mind that the squared return is a noisy measure of variance. You haven't yet seen it's noisy, so just take it from me for now, and we're going to talk about that more, later today. But that variance measure is noisy. And it would also mean that the forecast is prone to measurement errors. Because if you have measurement errors in the input, then your output, which is your variance forecast, will also be noisy. So it's not clear that that is a good idea. And one could find a smoother and hopefully more accurate measure of variance. Yeah. That requires us some additional work. Now, the beauty of R square is once you observe the price, you also observe returns, you observe R square. but it's noisy. Okay. What one also can do is one can extract the priced in variance from option contracts. That would be a forecast which we extract already, because the option is a contract that has a maturity from 1 day up to 1 year, 2 years. And demand and supply agrees on a price, and that price is based on the anticipated variance that the investors price in. And there's a simple way, we will talk about that in another class, on how to extract that. That could also be a variance forecast. But the point is that the variance you extract from options, they contain potentially a variance risk premium, which is also biasing your forecast. So there are different ways of making forecasts. They all come with advantage and disadvantage. For now, what you just need to keep in mind is the R-square measure for variance is noisy. It doesn't directly give you a forecast, but you could help yourself by fitting its time series to any type of model that you would like. If you don't have something in mind, just think about a regression. Okay. The next thing we want to do is we want to look at the GARCH variance. Last week, we also talked about the concept of a GARCH. And now let's take the GARCH variance as a backward-looking variance estimator. So we're still in the phase of the course where we do a lot of package work. So here we are relying on the ARCH model that comes from the ARCH package. Now let's exercise that. Now we load in that package. And what I'm now doing, I'm now calling the ARCH model from the package. I read in the return time series for which I want the GARCH implied variance estimate. I specify the order of the GARCH, so it has order P equals 1 and Q equals 1. That will have an ARCH 1 and then the auto correlation of sigma square, that's the Q. I can specify how to set the mean of that time series, and that mean shall be just a constant, because daily returns, there's no evidence for predictability. So just take a constant, get the level right. And then I say the volatility equation or the variance equation. You also see the package follows our concept that we have this mean equation, then we have this variance or here volatility equation. We say it's a GARCH, and the distribution of return shocks we say shall be normal, a Gaussian. So you could play around also with the t distribution and other distributions, but just make it a Gauss distribution. Okay. And that is what I'm now saving into the object basic GM, basic GARCH model. Okay. Next thing I want to do, I have this GARCH model object. Now I want to fit the GARCH model object. And I just say the update frequency for display shall be 4. I haven't checked what that really means, so that's our homework. I forgot, but you will see there's output coming up. And so let's do the fitting, and that will be our GM result. Okay. So let's just look at the output here. Yeah, it says terminated successfully. Okay, current function value. Iterations, gradient evaluations. So the estimation works with maximum likelihood. We talked about that conceptually last class. The numerical optimization uses a local optimization routine, which evaluates the gradient. Seems to be like a Newton type method. And then we have a warning message. So let's read the warning message. Data scale warning. Y, which is our return, is poorly scaled. which may affect the convergence of the optimizer when estimating the model parameters. The scale of y is 0.30. The parameter estimation works better when the value is between 1 and 1,000. The recommended rescaling is 100 times y. The warning can be disabled by either rescaling before initializing the model or by setting rescale to false. Okay, so what we learned from that is some warnings are useful. The usefulness comes from understanding that the warning is really about that the optimizer has a convergence criterion, and the convergence criteria is met pretty easily if the y is so small. Because the convergence criteria is usually on the spread on y, not necessarily y, but without looking to the package, let's just say the convergence criteria is some function of, let's say, the y. I say let's say because we're really fitting the variance, but it's an indirect function of the y. Why? Because the GARCH, on the one hand, that doesn't matter. Don't want to go into that. I think the punchline is just we have to rescale. All right, then we just do it, right? So we say thank you for such a good package, which even tells us what to do. So we just reinitiate the object. We are overwriting the object. I just use the same command, but I just scale as I was asked to do by 100. Meaning, magnitude-wise, I still have daily returns, but now in percentage units. Okay, so let's just reinitialize it, and let's refit, which is the same function then here. Okay. Iteration 4, you see the function count is already different. Iteration 8, you see it stopped iterating here because the convergence happened. But here it keeps iterating. The likelihood looks different. And yeah, let's just look at the summary statistic. We have a constant mean GARCH model. That's correct. Our dependent variable was the 1/n return, the market return. We have a constant mean in our mean equation. In the variance equation, we have a GARCH with a Gaussian shock. We estimate the model with maximum likelihood. Today is 9/12. Yeah, that's correct. Estimation was really fast. R square, adjusted R square looks 0, but all right. I mean, we did not do any predictions, just extracting the variance. Here's the likelihood, the log likelihood. Then we have the AIC, the BIC, number of observations, 5,000 roughly. Okay. That is the constant mu for the mean. Yeah, it's 0.06. So yeah, if you just take 0.066, and now I want to annualize in percent, so I multiply by 252 trading days. It's already in percent because the input is 100 times the return, which is in percent units. So you see the average return for the market would be, say, 16%. That seems high. Does anyone remember from class? Oh, I don't have the chat open. Does anyone remember from class previously? What was the mean of the market? I can't believe it was 16% if you just take the sample mean. That's interesting, something to look into. Just make a comment. Okay. What else do we see? We see an omega, we see an alpha, and we see a beta. So we should go into the GARCH model package in order to understand what these parameters are supposed to mean. GARCH model Python. GARCH documentation. Yeah? Kevin Shepard is a very famous econometrician. So he did the package, which gives, okay, great. So your introduction to the GARCH models. Returns have a mean and they have a shock, like we had. The shock has two components, vol and IID. The notation here, as I said, mine is a bit different. I have sigma t minus 1 in order to highlight it's known as of t minus 1. In that package, they use sigma t, but that's all right. And then you see sigma t square depends on the last residual of the return squared times alpha plus beta times. Okay. These are the coefficients which we just estimated. The omega, the constant, the alpha, and the beta. Okay. So the beta is really large, relatively speaking, 0.8. So it shows us as a high persistence in past variance. Yeah, 0.88. So if past variance was large, today's variance is also large. That's a sign of this, that vol clustering. And then in addition, the loading on return innovations is 0.1. So 0.1 of the past squared return is also going to the GARCH. What about significance? Yeah, T star is 8, the beta is 66. And the omega has a T stat of 4. Asymptotic standard errors. We have 5,000 observations, so that's asymptotic. Okay, so looks fine. Now let's just have a look at the conditional volatility. I'm not sure, I've never mentioned that. There is a nice command that you can use. Dear GM result. You see, if you take any Python object and you put that in parentheses and put dear, like directory, or I don't know what that stands for. If you put that in front, you see what is part of that object. Yeah, like here you can get the date time, get the index, is it a pandas, yes or no? You can get the log likelihood. So like a private member or like members, public members of that class. Number of observations you can get, params, the R-square, residual, volatility, the AIC criteria, the conditional vol, right? And that's the function we were using, or I'm about to use here, conditional vol. Okay, so keep that in mind, the dear. Because it might be that in an exercise, I might ask something which relies on you using a function which we haven't yet used in class. But if you could figure out which of the objects are useful for solving the problem, then using the dear command, you can check whether you find the input, whether you find the output function that you would need. Okay. Even has a plot function, the p-values, r-squared adjusted, it's the t-values. Okay. 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 So let's just plot, not just plot, but let's get that conditional vol. Here's the conditional volatility of the market portfolio. 135, 152s. So let's think about the magnitudes. We put in returns, we have a return series, which is put into maximum likelihood with a GARCH parameterization, and then it's estimated. The returns are multiplied by 100. So we give in daily returns with a percentage unit. And therefore the variance is also in percent per day. Let's just double check, yeah, 1.35 times, that's the vol. So the vol is annualized by square root of 252, if we assume 252 trading days. Well, then you get an annualized volatility for the market of 21%. Just like my rule of thumb, market variance unconditionally is around 20%. Okay. Yeah. Also, you see, for just looking at the numbers, that there are periods like here where the variance is twice as high. That's this right jump in volatility. It can move up really quickly here. 0.17, 16, and now suddenly it jumps up to 295. What's the relative spread? 295, 2.95 divided by 1.63. Yeah, you got an 80% jump in volatility, relatively speaking, within a day for the GARCH, which is already smooth. So unit jumps in that. What means unit jumps? Wait a minute. The GARCH did it. GARCH did it. GARCH did it. Okay. But why did the GARCH did it? Because we would have to check how the returns looked like. But to me, such a gigantic jump seems to be driven by a large return jump the day before. Well, let me just have a look. Let's look at the 1/n portfolio. And I want also detail. How many do I need? I need 1, 2, 3, 4. Let's take 5. Exactly. And I would here, that variance was from here to here. No, that variance in T was large. So I said the return on the 9th of November must have been really large, right? And that's what you see here. It was really large. We just go up again. Let's just annualize that return. We got 0.0768. That's the return. So we have to multiply by 100 times 252. What? Zero, 0.07 times 252 times 100 in percent. Okay. That's interesting. That's interesting. Because you have an abnormal return and then you annualize, right? And if you annualize, you just multiply that return by the number of time periods These are log returns. So it can just be, right? If you have let's say you have one day where you just earned abnormally much and you just made like here 0.07, that the annualized number is just gigantic. But it doesn't mean that you earn that return over the entire year because you just earned it for one day. So it could just be enormous. And that was my point, because I said before, how do you get on a daily basis a relative increase of 80% in variance? That cannot be something diffusive. So I said you need a jump. That for me here is diffusive, yeah, because it's autocorrelation of the past variance. That's something which is usually smooth. But the GARCH has built in that dependence on returns. If that past return is large, then boom, the variance jumps up. It's a parametric model. Keep that in mind. We don't know whether that is true because we don't observe the variance. That is always the mystery we have. Makes it complicated. Okay. Okay. Yeah, but at least just see. We move slow today, but I don't mind. Because if you do work in any type of data discipline, you always should double check and try to find inconsistencies. Okay, that is consistent. Yeah, we understand how the GARCH could make such a gigantic variance increase. Yeah. If that return would have been really low, something odd would have been there, but everything is fine. Okay, so I leave that maybe, yeah, and then I just upload that for you. It's not in the cloud. Yeah, so I make a comment for you. Note a large return on 1109 results in the relative increase of vol in the 80% relative increase in vol on 1110. Okay. Okay. Now, isn't it interesting that we have now two measures for the variance of the market? To also ask, how similar are these measures to each other? Because ideally, they should be giving us the same solution. Whenever you work with a model, keep in mind all models are wrong, but some are useful. Second thing is, the more you are in the data science sphere, the more you like non-parametric models, model-free approaches. So how to get the variance in a model-free way? That is a question I posed here. That's a question that stays with us. Keep adding your insights. For the moment, we start simple steps with parametric models. They were worth a Nobel Prize. So it's also worth looking into that. And for these parametric models, you see now they will give us different results. Because I'm here checking the variance method 1, which are squared returns, and I compare that to the conditional volatility power of 2, both applied to the equal weight portfolio. Any idea of how large is the correlation? I take the betting. Just try to find your chat. Here's the chat. Oh, wait a minute. I'm sorry, I didn't see your chat. Now I see the chat again. There is some delay, at least on your camera. Yeah. I also saw that now with my iPad. I see that really. I can observe myself. There was the delay also in the past. I just wonder whether I should turn off maybe my iPad. Am I the only one who can't see the prof's screen? 8:35, that's 1 hour ago. I apologize for responding so late. I hope you can see it by now. If not, you just have to speak up. I can see it, that's good. Try in the code cell. Oh, I see, okay, I was too late. You please zoom on your screen. Yeah, on my iPad, it's also small. On my laptop, it's large, so I don't know what you see, but I don't know, even if I was wondering once, but even if I magnify on my iPad, but maybe the iPad is frozen, doesn't change much. You see, internet connection is gone. I just turn off my iPad. Boom. Okay, I think that is too large, but I think I can go like that. Don't we have log returns? Yes, we have log returns. I don't know, what was the result? And we multiply it by 100, we take the return. Exactly, right? That was the point, what I meant. If you get a large return on one day and you annualize it, the assumption will be that you're going to earn the same return over and over again and even earn interest on interest. That's why it was a good exercise now by accident, but that's why I want to do some data work with you to come across these accidents, because I don't think about these accidents ex ante. That annualization is not innocuous. Yeah. And one example would be, let's say you make a wonderful trade. It just earns you 10% on one day. Awesome. Now, if you annualize that, you have 10% times 252. So you have like a 2000% annualized return. But if you don't do anything else in that year, you will end the year with just 10%. Right? So the annualization just really assumes exactly as the student said. Here he said it in terms of the return to the power of 100. That would be if you have geometric returns. But it's just a matter of interest on interest, which we could ignore for the moment. So that's why this return of 1,900 was so huge. And I was like, oh, what's that? Yeah. So then I had to think about, all right, it's just I annualize that extremely abnormal return. I think the delay was there before. Okay, thanks for letting me know. I just didn't know. On my laptop, it is fast, but on the iPad, I saw today the first time there is a latency, which is not that nice. Okay. Okay. That is one reason why I speak slow. Already last week, I started to speak very slow. And today, I also want to speak slow to overcome the latency. Okay, now let's take some bets. What's the correlation in your mind between these two methods, squared return and GARCH? Not about getting it right, just about, let's see what your prior is. Maybe you've seen it, maybe not. Can someone, maybe just two people at least? Is it around 10% or is it around 90%? Or is it around 50%? I think we have like 3 points. Someone says 0.4, 0.6. Okay, so somewhere in the area of 50. Why? What makes you think it's, if we have 3, 0.3, 0.6, 0.4, so the average is like 0.5 maybe? Why do you think it's just in the area of 0.5 and not in the area of 0.9? That's part of the training. Because of shocks, but can you be more explicit? What means because of shocks? Those large jumps we saw earlier. But that again is not yet precise enough for me. Which jumps do you mean? Jumps in return or jumps in vol? We kind of saw both. Some of my comments are just to tease you, but I hope that fosters learning. Jumps in vol. But how do you know there are jumps in vol? Yeah, please keep going. Benjamin, let's just keep going. How do we know, or how do you know? And you're the brave one. So how do you know that there is jumps in vol? Otherwise, I think we just would have the clusters. Okay, what I'm after, you're very, very close. You know, I just try to tease to learn. Well, jumps in returns, equated jumps in model vol when exactly, right? Exactly. So we just believe there are jumps in vol by having used these squared returns as our first measure. I could have started with GARCH or SVM, but I wanted to start with the simplest one. So basically, because there are jumps in returns, they translate into jumps in vol using that measure exactly. And if you looked carefully here, the squared return measure would be omega is 0, alpha is 1, beta is 0. Right? Because ignoring the mu, epsilon square is r square. If mu was 0, it's not 0, but it doesn't matter for my analysis as of now. So you see, if the alpha was really large and the beta small, GARCH and the squared return would be similar to each other. In our estimation, the alpha is only 0.1, right? So only 10% of the 1, which already highlights that these return spikes or these return jumps, which in the first method for variance translates into variance jumps, should not show up that dramatically. They will show up, but with a lower magnitude. So let's just see. Yeah, 37% is the correlation. So let's just have a plot. We use matplotlib. We have a nice graph, and I want to plot the annualized conditional volatility in percent of the equal weight portfolio. I want to use a GARCH versus the R square. So what I do is I just plot the index. That will be the time series. And I started with the pandas data frame. I squared it. So I put that into the GM, into the GARCH. So the index is not lost. If you remember when I made the dir function, it also showed index. So the index is a function of the package. And then it gives me the conditional vol, and I multiply only by 252 square root. Because when estimating the GARCH, I multiply the returns by 100. Need some additional water. Okay, great. Okay, all right. So here you see annualization. And the next plot will be the index. I could have used the same index, just used it for here, but they have the same index. And then I take the square root of the annualized variance times 100. Okay, and that will be my R square. Now, one student just wrote again in another context that the R square was not a good estimator, right? When you look at that, R square is part of the GARCH, yeah? So that can be rationalized, which I mentioned already last class, which I like. But if you translate back to volatility, you kind of see it's really awkward, or it's really quick and dirty. It's really dirty because if I take the return square, which is my variance measure, and then I take the square root out of it, I'm back at square one. I'm back at my returns. So you see vol and returns are extremely closely connected in that method, which is likely not true. But it's a valid method, which you often see also in research papers, especially if people have no other measures at hand. And here's what it looks like. Annualized conditional vol, it's annualized. GARCH versus R square. That's for the market. All right? Here, maybe we start with the COVID. COVID, if you take return square, you have a variance of a vol of 250%, while the GARCH implied is at 80% or at 90%. Huge differences. Yeah, you see, noisy, yeah, means kind of very spiky, away from the true, but of course we don't know the true, a big problem. But for sure, the vol cannot just be the return. So you kind of see the GARCH is, let's just say, give you some, from a research perspective, we know GARCH is the better measure. You really kind of see the quick and dirty approach. It gets the overall shape, but it's really noisy. It's really noisy. Yeah, like financial crisis. The GARCH implied vol looks like an 80%, looks similar to the COVID. Yeah, while the return spread is different. So that's what I meant before when I said COVID vol is twice as large as financial crisis vol. That was for the R square measure. You take the GARCH measure, they're at the same level, roughly speaking. Also here, financial crisis in Europe, we have, I come to the point which is coming up in the chat. That's a very good one. We have Euro crisis like 50%, and the R square would be 100%. Okay, right? So measures are different. Let's go to the chat. Okay, so there's a wonderful comment in the chat, or let's say one wonderful question. Shouldn't the return be shifted, so the R square be shifted by 1 day, because for the squared returns, we use today's return to calculate today's vol, but for GARCH, we use yesterday's returns to calculate today's vol, don't we? Okay, what is the GARCH doing? We used a package. So the disadvantage is we didn't program it ourselves. So we need to understand the package. Here's what the package does. The maximum likelihood function is not shown here, but I showed that last class conceptually with the LaTeX formulas. So what the package is therefore doing, it just translates that equation 1.1 with the others into a maximum likelihood Gaussian density, which it maximizes to extract out sigma t. Now, you therefore see that the sigma t that comes out is the vol that corresponds to the t, to the RT. So the short answer will be the indexing here is fine. We don't have to reverse and we don't have to lag. Because when we square RT, let's ignore the mu for the moment. We have epsilon square, which is sigma square times something which has a variance of 1. So you see that the R square and the sigma square have the same indexing. So we wouldn't have to shift that. But thanks for mentioning that. That's really important. Yeah, keep coming with these things. I think that's a big advantage that we can discuss that. As you are good in reading and doing yourself things, I think we should really discuss more. Okay. Is that fine? Okay. Okay. So let's go to a single asset perspective. Again, I like to go to the market first. It's an aggregation. There's less noise involved because of diversification that happens. And let's just go to a single asset. And I also want to compare the correlation of the GARCH vol with squared returns. Now, let's just redo what we've done. We initialize an arch model using the package. We already learned from our prior warning. We use 100 times the return. Here we take Volkswagen. We take a GARCH 1,1. Mean equation is a constant. The vol is a GARCH. And we take a Gaussian error. Okay. And then we also fit that thing. Okay. And now we get the correlation between the squared return and the GARCH implied vol, both in terms of variance. So we correlate both variances, only 7%. So they have nothing in common. Nothing in common. It should be that way. Why? That's why I come back to that financial decomposition. The return shock is the product of the vol and the fundamental shock, right? The vol is like the potential, and then there's the economic news which kicks in. These are two separate animals. It doesn't have to be the same. And that is just what you see. If you square the returns, and if you have extreme returns, because you have extreme shocks, yeah, it's like the diesel scandal. I mean, prior to the diesel scandal, why was the vol high? I don't think the vol was high for Volkswagen. It was just a scandal that these guys come in like, hey, there's fraud involved. And then the price moves down, meaning negative return. If you square it, you would then have a large estimate for the variance, right? And that's the disadvantage of that quick and dirty measure. Using a GARCH, using a maximum likelihood estimation, you get a more accurate outcome. So let's just plot these things. It's the same function than previously. So that's the GARCH versus the R square for Volkswagen. And I mean, the overall theme is similar. Again, we could just check why it is similar. Why don't we do it? Does someone, we are not in the cloud. I wanted to ask someone to do it. Let's just get the, parameter estimates of the GARCH. GM result Volkswagen. What am I doing here? The 7% told me there's nothing in common. Now I look at the time series and I'm thinking, well, it's not too bad because, you know, the spike is here on both sides in a sense, in a way. So it seems to me they have something in common, but still, you see, like here, you see so much like movements in the return square, which just the GARCH rule says nothing happens. So I believe the alpha coefficient is not 0, but maybe it's 0.05 or something like that. No, it's 0.11. You see, like with the market. So it's interesting. The GARCH coefficients are similar to the market. Similar, yeah? 0.8, 0.1. But the magnitudes are lower. Okay, which gives such a low correlation. Yeah. And I mean, if you take return square of the short squeeze, you have an annualized, a ridiculously high annualized vol of 1,400%. For the GARCH, which is the state of the art in the literature, it's still suspiciously high. It's at 500%. Enormous. So you see the trouble of not observing the true volatility. How can we say which one is correct or not? Okay. Now let's make some summary, a bit of summary here. Observations and implications for GARCH market and for the Volkswagen variance. So what have we learned so far? We saw that the GARCH versus the squared return variant for Volkswagen is, I put completely in high commas. 7% means completely in terms of correlation. In terms of time series, it's a smoothed version of that, right? And it's clear where the smoothing comes from, the 0.1. Yeah, we just down weight squared return innovations, but they're still there. And it will be different than to the stochastic vol model, which does not, I was about to say, mechanically tie down the variance to return shocks. For the return shocks, as we see, they have an impact of 10%, roughly speaking. It's not clear that is good. The difference is because realized returns are the product of vol times shock, and the squared return method ignores that and assigns periods of low vol with high return shocks to coincide with high vol periods. Coincide, right? So the idea is you could be in a period of low vol, but then a shock comes in like the COVID. And now this R square tells you also vol was high ex ante, and even GARCH will tell you vol was high ex ante. Mechanically. Why mechanically? Well, because if the alpha here is not 0, then there is return innovations translate into vol innovations. And it's hard to say for 100% accuracy whether that is correct or not, right? Because that's a parametric model. We just allow the optimizer to set the alpha to 0 or to a positive number in order to fit the likelihood of returns. So we don't fit the likelihood of volatility. But if you think in terms of supervised learning, the supervisor is realized returns. It's an indirect measure of variance because we try to learn the second moment, which is time varying, by using the realized value of the distribution that has a first, a second, and a third, and a fourth moment. It's very indirect. Very indirect. But you have to see it from an evolutionary point of view, right? That before the GARCH came out, people used the R square as a measure. And then Bob Engel came, took this idea, I believe, from the bio science field. And so they moved on, right? And that's also how we do it here. So the short squeeze vol is still at 600% for the GARCH. it makes me curious whether that's correct or not. We keep an eye on that. Now, the implication, me personally, I would not use squared returns as a variance measure if I need a robust estimate. Right? If I just need a quick view on the time series, I would do it. That's why I've also done it in the class. But if I care for the magnitudes, I wouldn't. And I gave you these two examples, the market and Volkswagen, to see for yourself and make your own opinion. That's just an opinion. And the other implication, it's hard to say which measure is right, as there is no true observed measure in data. Right? That is. And it gets even worse if you look for higher moments like skewness and kurtosis. That's why it's good to really spend time on variance, appreciate what it means that that object is not observed. Now, the GARCH allows us to make a forecast for the next periods. Why? Because it's a parametric model. Yeah, if the parameters are estimated, we have a time series for the conditional volatility or the conditional variance, and we can also extract the return innovations. Therefore, you see, you can iterate forward. Let's say if that would be the last variance in our training set and the last return innovation in the training set, you just take these last observations, multiply by beta, alpha, omega, and then you get your variance forecast for the next day. So it's a parametric forecast, as we are using a parameterization of our return model to learn about the unobserved variance inside these returns. Again, keep in mind that is just the second moment of these realized returns. That's what I meant with the indirect supervisor. A stronger supervisor would be if we observed some deterministic function of variance, where we knew the deterministic function, but we don't. That makes it complicated, and that makes it necessary to always ask for robustness. Let me go to the chat. How do we know whether GARCH 1.1 with a constant mean is the correct specification? Exactly. How do you know? Now, what can you do from a data science perspective? You can change the specifications. If it's about the mean that you vary, you can change specifications of the mean. And you can also change that. And then from a statistical point of view, first thing you do, you check whether the likelihood is different, is higher. I stopped because if I change the P and the Q and also the normal, then of course I also change the likelihood. So that's not the best comparison. Because you got more parameters to estimate, right? And you don't penalize the likelihood for the number of parameters. But you have the AIC criteria, the BIC, so that these are likelihoods which penalize by the number of parameters. So you could look at that. I wouldn't do it. I don't think that's a fruitful way to go. The fruitful way to go, I mentioned the current zeitgeist, is keep it simple. and use domain knowledge. You need domain knowledge. So I think you also take this class to get a little bit of finance domain knowledge. We have the domain knowledge that daily equity returns are not predictable. You could check that simply by fit an AR1 to daily returns. You will see the AR1 coefficient is statistically speaking 0. And therefore, you know that a constant in the mean is sufficient. And then, zeitgeist, keep it simple. Today, researchers don't play around with a GARCH 2, 5, and 8, 10. When I was a PhD student, they did. But now they don't. It's, you know, I mean, that's why I like the way we move the course, also with the data work. I have an object I want to learn about, which I don't observe. I use the likelihood function of a parametric model on returns to learn about the GARCH. It's indirect. Now, using higher parameterized GARCHs has the danger of data mining. So I wouldn't do it. Zeitgeist doesn't do it. Therefore, your question, Benjamin, that one I answered. That one is the one that is potentially critical for applied work. When I see practitioners do the work, they deviate from a Gauss distribution. They use a t-distribution in the shocks, which I think is better. Because we don't know what the shocks are. But again, use finance domain knowledge. We know returns are fat-tailed. A t-distribution has fat tails. If we have a Gauss distribution with a GARCH, we also have fat tails. So that's why we can still work with the Gauss, which that's why I also do. And research, we also do it because first order effects are the same, but for industry, I've seen people then using a T here, and you could just change it in the package. But again, come to your question, how do we know it's a correct specification? I think everyone should ask that question. From what we've done so far, we will never know because vol is unobserved. I have a couple of bullet points at the end of this notebook about the literature, and then I come back to your point. I want to keep it open on purpose in the Socratic way, right? To really make you feel what it means, what this unhappiness kind of makes with us, that we can never be sure. How about cross-validation? No, it's not a property here. You can. What means cross-validation? It means if that is your training set here, yeah, you take a specific set out, which you use to learn some of these hyperparameters. Sure. But again, it's against the zeitgeist. But for a reason, what I meant before, I just don't know what you get out of it. To suddenly say it's a P2 and Q4 GARCH. You know, it wouldn't excite me. Why wouldn't it excite me? Well, we had a very good student recently as a research assistant for over half a year. He worked at the Forschungszentrum Informatik as a master's thesis writer, and then and he did this neural network exercise we did with the two informatics students, Jonas and Fabio, and PhD student Simon, who's now in industry. And his task was to extend that to fixed income. Yeah, so we gave him fixed income options, fixed income futures, and just copy in what we've done in the equity space, just do it for the fixed income, and let's just see what comes out of it. Because for the equity part, we learned the model does really well, for daily returns. So of course, the thinking was hopefully, or not hopefully, data scientist. I don't care. Let's just let the data speak. There was a prior that maybe it works, but there was a bit of suspicion there. And then he's doing all of that, the neural network with option-implied information, so on and so forth. And he shows that in the training set, things look good. Then he goes into the out of sample and it just was terrible. It was terrible. Okay, thanks for letting me talk about that. Y versus R in bonds. Let me just make a comment, stationary. For the neural network. Because we had a problem there. The problem was that the split, you take also this 80-20 split, or if you do cross-validation, you have maybe another 10 or 15 for the cross-validation. Now, if you look at the time series for interest rates, they kind of move like that, and then Euro crisis here, they go to 0, and then here they are basically 0, which means the neural net and everything, we trained that on yields. The neural net trained here, and there was a complete regime shift in our test set. That's the worst that can happen. That's why I always still have to smile. We have to find a solution for that, because that is what happens in the domain finance. There's a regime shift. The regime didn't happen before. We never had 0 interest rates. The machine, although we had this neural network, but it's a parametric way, a parametric model for the density. It's learning based on a time series, and we had cross-validation, everything, but doesn't matter, right? The cross-validation was then somewhere here. And in the test set, just our input was basically 0. It looked very different. It's not important that it was 0. It's important it was flat. So whatever the neural network learned before was then to make a flat forecast. I don't know whether that is now correct with the flat forecast, but it just didn't work. It was very disappointing. But just tells us we have to think. And now what I just wrote down is maybe we should use returns. I went to yields because yields are less noisy, far less noisy. But for returns, you see, right? They're just moving like the heart rate if you drink too much coffee. I think we should redo it with that. He did it first and it also didn't work. And that's why I told him go with yields. But maybe what we found here, the problem is gone with returns. I don't know. But just interesting for you, we learned that if you take an AR1, an autoregressive first order forecast for interest rates, it's better than if you take a neural network with option information inside and everything like that. Yeah, it's again domain knowledge here then for the specific asset class interest rates. And interest rates are like volatility, very persistent. So if you care, make a project, because we have all option data which is out there. And this neural network thing is a library basically, which you can start plug and play. You don't have to develop. And my thinking is that volatility are a mix of equity returns and of interest rates, because they are persistent. Yeah, even here in the GARCH specification, you see the betas, they were at around 0.8. Yeah, so it's persistent. We will have other estimation approaches coming up today where the autocorrelation in variance is 0.99. So it's highly persistent, exactly like interest rates. And then there are options out there on volatility. And therefore, we could also use a neural network, exactly copy the same approach to ask how to best forecast volatility. So really, Benjamin, thumbs up for your question. Keep coming with these questions. It's really to your own value. Because even if you have a professor or an industry person who is more bullish in the presentation and he tells you that is the best model for vol, that's wrong. Just wrong. If you don't know, if you don't observe the supervisor, you will never know. You always have just indirect tests. And that's a challenge, right? Okay. Right, so, but I mentioned something for research, which is even not yet done by anyone using these neural networks. with time series and option. For example, what could one do? Like we did with returns. We could use, I like it. I think it's an awesome project. And it's not difficult because there's so much already developed, but there's still some stuff to do. Now, you ask the question like Benjamin does, how do we know the model is correct? Now, what I learned from the neural network exercise with Jonas and Fabio and Simon is the neural network can tell us in terms of if you give in the GARCH vol as an input, you give in the R square as an input. They're not highly correlated, so it's not a multicollinearity problem. And you give in whatever other time series measure you have, and you give in the option information like we do. And then you ask the neural network to learn. I have to smile because you need a supervisor, right? Again, the supervisor is not observed, but it affects everything of what the neural network is going to learn. That's why I stop and smile. That's what I meant. There's a little bit to do. We have to think about what is the best supervisor here. I don't know yet. I don't know yet. Because if I say it's the GARCH, then of course the neural network goes for the GARCH. Right? You see the point. If I say it's that, it goes for that. So it can't be that. That's why I tend to think to go with the options, because that's a price which I observe. So it's a different exercise there, but maybe that's what I mean. There's a bit to do, but not too much. We can do that rather quickly. And then one asks, if we agree on the supervisor, which you see here, what's really is the challenge of having an unobserved quantity as a supervisor, the neural network will give weights on these different inputs. It's like a regression with these coefficients here, right? And the neural network is just a non-linear regression, which gives then weight on these different inputs, be it the GARCH vol or the other vol. And that's, if you have the perfect supervisor, it will tell you which of these different parametric models are the ones that have a high weight in the neural net. And that is how we started the neural network exercise with these informatics students. We said research shows, or teaching shows and research, that returns cannot be predicted by backward-looking data. And option research shows it can, right? And then when the informatics students started doing that, they once sent me an email saying, it's so interesting what we find. It's exactly as you taught us in class. All these backward-looking features, like the Fama-French factors, past returns, are set by the neural network to 0 in terms of the coefficient of this regression. But these option-implied, they have a positive weight. Right? So that's a kind of data confirmation of finance domain knowledge. That's why just doing, like someone had this Kaggle challenge, which again, keep coming, all that stuff. I think it's very interesting for everyone to look at that. I also looked at it. I'm suspicious. I just went there 3 seconds. But what I saw within 3 seconds, I hope it's correct, is that they eliminate the name of the features, which means they eliminate the domain knowledge. And that means if you find something, they can use it for their own trading. You cannot, because you don't get the numbers in real time later on, and then you don't know what you've learned. And on the other hand, since there's so much noise in finance data, this domain knowledge is really important. Yeah, like I said before, interest rates are so persistent, equity returns are not. And vol is persistent. And that, if you know that, it affects how you would try to tackle the forecasting exercise. Although I get it, if you're extremely good and have so much data, you might figure it out. But that needs to be shown, that I haven't seen yet. Because ignoring domain knowledge just means you're potentially inefficient as you spend resources on stuff that you know ex ante doesn't work. So what about we use the GARCH, stochastic vol and implied vol, and then do a PCA to find common core movements? That's an excellent question. That is something I want to go for in the problem sets for you. Exactly. I mean, that's already prepared. That's exactly. Keep coming. I think we have to discuss more. Otherwise, it gets too passive. Yes. I don't see your name, unfortunately. That's exactly what we will do. That's exactly what we will do. Yeah. Okay. So I assume if you need a break, you just go for a little break and then come back, right? Let's continue. As I go so slow, I think you can always connect back. Okay. So we spent now, I think, quite amount of time on that question from Benjamin, but I think it was really useful. I hope it was useful for you. Not let me know. Maybe I spoke too much about it, fast, whatever. I think it was a very good question. And I hope it was a good answer. Okay, so here I gave you an example. If you want to make a forecast, as I said, okay, that's just a summary. Okay. If you want to get a forecast, yeah, you look at the tail. You see the last observation for the volatility we have is it's annualized already. It's 40% in November. So, and then if you want to forecast for the 13th of November, then you just take the estimated parameters and the last conditional vol estimate from last conditional vol and return innovation estimate. You need both. And then you iterate forward. Yeah, I don't know that package. So let's just see GM result, whether because they should already have a forecast. That's the conditional vol, that's the current vol, the spot volatility. Forecast. You see there's a function for forecast. I just don't want to use it here. I haven't tested it. It looks like you just do forecast, but you need to specify the forecast horizon. So that's something if you want to play around a little bit at home, what you could do, make a forecast for the next 10 days and just plot that. Okay, it's there. Good. Now, GARCH implied vol time series is a deterministic function of past return shocks. Now here, it's a deterministic function. There's no additional stochastic innovation. That is just autocorrelation. And that is the return innovation, which gets multiplied by a constant, so it's deterministic. And that's a parametric model. And all models are wrong, but some are useful. Right? So empirical research, that's what I just tell you, shows that option-implied volatility is driven by shocks that do not drive returns. Going back to the question about Benjamin, you see, I like to call names. That's why I could have also taken UCSEB, which is hard to pronounce. The reason also literature goes to options, and I want to move in that class to option, is options are at least an objective supervisor. It's biased because of a premium, but still, at least it's an objective measure. And I can use domain knowledge, like valuation theory, to help me eliminate the bias. And if you take option volatility, and we will do that, that's my promise. That's why I need to keep an eye on time and so on and so forth. But that is my most important goal for the course. As the last comment in the chat says, we will look how strong is the correlation between option vol of firms and the underlying parametric time series approaches that we talk about. And we will also check, we can do that, whether this option vol co-moves with return innovations. What you can do is, since vol is so persistent, you just fit an AR1 to vol, you get residuals, and you fit a return to an AR1, get residuals, and correlate these things, these residuals. The correlation is very low. And this just tells us that option vol is not driven by return vol. And if the bias in options is not that big, which we believe it is, and I give you evidence for that later on, it kind of also indirectly tells us that volatility should have its own shock, its own innovations. And the GARCH cannot deliver that. Right? But when did options start to trade? Of course, in the 80s and so on, but really the data we have, they start in 2002. GARCH was developed in the mid 80s or early 90s. I don't know even, I would say mid 80s. So you see, right, it took 20 years of getting better data, getting better supervisors, and then improve. But still, GARCH is a standard in industry and literature. But there are other standards also. One is the stochastic vol model, which I want to talk about. Awesome. It's just also Carnero 2004. That's not some big important paper. I just thought it's interesting. Finds that in GARCH models, the persistence parameter, that would be the beta. Yeah, the persistence. It affects the mean reversion and also the kurtosis of the time series. And in stochastic volatility models, both of these features can be modeled independently. Right? So don't read the paper unless you really want, but there's no need to. Just as an academic, I wanted to give you a reference for the claim. And I just used the claim here to motivate why we move on and not stop with the GARCH. Point is here, you can have a time series which reverts fast, but still have excess kurtosis, right? And apparently in the GARCH, you cannot separate these two features of data separately, but only jointly. And the stochastic vol model allows us to disentangle these features. Okay. Another thing is questions like, how do returns change next period if vol goes up? Cannot be answered by the GARCH. Right? If you, for example, say now I'm in such a stress period or in such a calm period again, what's the implication then for returns? The GARCH gives no answer because the GARCH is a deterministic function of returns. But the stochastic vol model, it allows us to answer such a question. It allows us to disentangle mean reversion kurtosis, and it allows us in a straightforward way price also options on top. And I did some reading for the teaching here, and I also read, I don't have the citation here, but I can find it if you care for it. I found that the SVM, they say the stochastic vol model is also very well suited if you have a multi-dimensional data panel like we have. We have 42 firms, so we have 42 GARCHs. And if you did a problem set, you know there's a low dimensional factor structure most likely. Now, how do you implement a factor structure with a GARCH? That is not so straightforward. For a stochastic vol model, it's more straightforward. So I just tell you, while I like the SVM, I also like the GARCH, but I can see that a statistician comes along and just says he likes GARCH better. That's all right. These are two standard state-of-the-art approaches. Yeah, but I also want to talk about the SVM. It has its merits. Okay, so I want to finish the SVM today. I apologize for the coughing. Okay, let's just see. We do some theory, and then I jump into the data work. And then I give you a problem set if you like to do it on SVM on NSS. The student said here, the last comment, maybe about comparing the PCs of these different approaches. But now I want to talk about the SVM. Here, Stochastic Volatility Model. Now, it's just another parameterization of the sigma t times ct. Yeah, you see my GARCH notation of sigma t here is now consistent with the literature. I say the mean return. It just means if your returns have a mean, yeah, going back to maybe again Benjamin, who asked whether the constant mean is a good specification. You can always subtract the mean in the first step from a return, either be a constant or you run an ARMA model or whatever model you want for the mean equation. And then you end up with, so to say, the residuals, and they are mean zero. And now you fit these to a stochastic volatility model. And that stochastic volatility model, it's in the univariate form, just says we have a Gauss shock here, and then we have vol, and vol has a constant times the exponential of 1/2 times ht, and ht follows an AR1 process with a Gaussian shock. So you see now the volatility itself is driven by ht, and ht is driven by eta t. And eta t is a different shock than that zeta here. So you see that volatility has its own shock. That is the core difference to the GARCH parameterization. You can allow the zeta and the eta to be correlated. That is all right. If you estimate such a model, okay, you can have them correlated. Okay. Now, we started with R square because it's so simple. We talked about why it's not the best. We continued with the GARCH, which is a maximum likelihood approach. In the past, all our students had to implement that themselves. Now, with the more data perspective, we do ask Python to do it. So you didn't feel it's more complicated. But it is, right? Because there's a package, it involves maximum likelihood estimation. And now it gets even more complicated because there are several methods and all of them in order to estimate the process. But all of them are more complex than the maximum likelihood of a GARCH. That, in my view, is one reason why a financial econometrician likes working with the GARCH. Just simple, yeah? MLE. But here we have to do something else. What can we do? There are different ways. There are so many different ways, and they're all more complicated. So I talk about the simplest way. And you will be excited, I believe, moving forward, because that simplest method invites us to study a very general concept, which if you take any machine learning book, not the simple ones, like the Tipeshani Hastings. But if you take, let's say, Bishop, the Bible of machine learning, there somewhere, I don't know, in the last 2/3, it's about the Kalman filter and expectation maximization algorithm. And I'm really happy that although we followed the data flow, that it invites us to understand with a practical application how filtering works, how a Kalman filter works, how even the linear Kalman filter works to a nonlinear problem. And the Harvey, he's a finance professor. He came across a finance problem where he wanted to model the volatility of different exchange rates. And he didn't want to use the GARCH because he wanted to use a multi-factor model for the vols. Yeah, like there are 1, 2 factors which drive all of the exchange rate variances plus some idiosyncratic noise. And that is difficult to do with the GARCH. So they did that with the SVM, and they apply a little data transformation trick, and they basically discovered the easiest way of filtering out the volatility. If you followed what I said in the past, today, an hour ago, I said returns are indirect supervisors for the HT. Yeah, because write that up here, you see the RT, the HT affects the second moment and also the kurtosis. But then you're drawing, think about if you simulate it, you are drawing from it realized returns. It's an indirect supervisor for what you really want, the HT. And if you know a little bit about the linear Kalman filter, you know that it only works if the HT would go into the drift, right? Then you would, because if you have something in the drift here, then the RT would be a direct supervisor. Because if the drift goes up by 10%, most likely the next realized return is also high up by, on average, 10%. But if you increase the variance by 10%, I don't know. I mean, the next returns, they are just more noisy, right? But they don't have a direction which the Kalman filter needs. And Harvey, what he's going to do, and we cover that later, he is just making a little data manipulation to get the HT into the drift. Yeah, how to do that? What happens if you take the log of the left-hand side? You have the log of that plus the log of that, and the log of that is the log of that plus HT times half. So you see, with that little trick, you just open up a new avenue of a well-studied procedure. And I love it so much. I want to teach that all the time because it teaches you also try to be creative when it comes to deterministic transformations of a problem in order then to use a heavy machinery which is well developed. It's very smart, basically. Okay, but we come to that. Now, just give me a bit presentation. What's the advantage over the GARCH? Well, empirical research finds the vol shocks are not linear functions of the underlying. In finance terms, people were asking whether you can hedge an option portfolio with the underlying. Let me repeat that. Can you hedge an option with the underlying? Chat is quiet. Anyone took a derivatives class? If so, please answer the question. Can I hedge an option with the underlying? So can I hedge an S&P 500 option with trading in the S&P 500? Okay, one person shows up with not only with the underlying. What else do I need? When you say not only with the underlying, what do you mean? What else is needed? Risk-free asset. Okay. Now, let's say the interest rate is 0, which it is as of now. Then you can ignore the risk-free asset. Okay. 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 So the answer in the chat, I thank you very much. Would be nice to know your name. I thank you very much for your answer. It's what I expected. Why? Because in the derivatives class, it's a theory class. And in the theory, you can make up a theory. All theories are wrong. Some are useful. Now, there's a useful theory, which is called Black-Scholes, got the Nobel Prize. It's useful, but it's not perfect. Now, in the Black-Scholes theory of option pricing, the option changes, the value of the option changes because the underlying changes. Now, let's give some statistical language. In Black-Scholes, they argue that the stock return is log normal. Or the log return, our R's are Gaussian. We do the data perspective here. Are log returns Gaussian? No. Okay. Does the volatility, like a log normal return has a constant volatility? Okay. And that means in Black-Scholes, the only input to the option that moves around is either the risk-free rate, which here we set to 0, and the price of the underlying of the stock itself. The vol is constant. If you look at the data and what all we have done today and in your problem set for today, there is just 100% evidence that the vol is time varying. And therefore, thanks for participating with the answers. In the derivatives class, you learn that options in the Black-Scholes world can be hedged perfectly if you can trade continuously in the stock and in the bond. But that is based on the model is correct. In reality, that's what research have been doing. They've been asking the question, can I really hedge an option with the underlying? And you can't. Why can't I do that? Gee, look at the data, because the volatility moves stochastically. So in order to hedge the option, you need, what means hedging? Make the option return be 0. Create a portfolio that has the option inside and the hedge such that the overall return is 0. And that doesn't work with the return. That's why I was asking you, not only with the underlying. You need something that captures the movements in volatility. And that is how we know that volatility is driven by shocks that differ from return shocks. Because if volatility shocks would be driven by return shocks, I would be able to hedge the option by the underlying. Because although vol moves, it moves in the same direction, or not same direction, it's directionless, but it moves by the same innovations than the underlying, epsilon square. But it doesn't. Okay, right, and in the course, I want to provide some evidence for that. I'm not sure we get there. And how can vol shocks be hedged? Awesome question. Awesome question. Excellent question. I mentioned the project, which awesome question. How do you know? Let's just how to hedge volatility. Yeah? You come up with questions, Google, and then double check with me. I mean, I know the answer, but I'm going after something in particular. Hedging volatility risk. Okay. Then let's do how to hedge volatility Eurex. Yeah, let's just take an exchange. Yeah. There are derivatives on volatility. And there's also a futures on the V stocks. And that's exactly why I restructured the course I'm doing as of now. It's this balancing act of moving towards concepts I didn't teach in the past. But if we do this financial data science in a realistic way, that's why I love these questions. And I hope you come more often with these questions. You just see that there's so much exciting stuff out there, which goes far beyond just equity investments. But we can learn from equity about finance domain knowledge and then move on. But there are futures on vol and options on vol. And these, the selling point, why the exchange offers that, that's why I was Googling just that way, is they are arguing it is a cost-efficient way to get the most accurate hedge against exposure to European volatility. Right? I think it's so exciting. I don't think we can do all of that in this course. My philosophy is I try to get slowly to as far as we can get. And if you then get the hook, then we can always find individual projects or group projects to deepen your understanding. But why don't we just read that? In a price drop in equity markets, VSTOXX futures can take a long position in the market while simultaneously hedging against downward moves in the equity market. In a price drop in equity markets, VSTOXX futures can take a long position in the market. I know that's somewhat weird the way it's written. This vol index, VSTOXX measures the implied variance across all options of a given time to expiry. The VSTOXX index features a negative correlation with the Eurostoxx index on a long-term basis. That is what I meant here. There's a correlation between return shocks and vol shocks, and the correlation is negative, also called leverage effect. Okay, yeah, you see, they talk about that. The SVM would take care of that. Because of this correlation, VSTOXX tends to move to the upside when all other asset classes are in decline, as indicated in the chart. That's correct. That's absolutely correct. Right? If the stock return crashes, all else equal, because of negative correlation, the vol shoots up, and therefore a futures on the vol or an option on vol goes up. That's a hedge. It's a negative correlation asset. There we have it. But you need to go to derivatives to get it. And the Eurex offers this, and we have the data because we just have all the Eurex data on a tick-by-tick basis. And we do at our chair, just all the work we do as of now is related to that option data set. It's enormous. It's extremely exciting. No one has it because it's you just can't pay for it. It's, I don't know, it costs like $1 million or something. The KIT has it traditionally, and we are working with it. We're not just working with it, but we do really, but I don't want to lose time, but yeah, it's our baby. Okay, so because of this correlation, the VSTOXX tends to move to the upside when all asset classes are in decline. Therefore, the VSTOXX has proven to be a relevant hedge in times of global crisis like 2008 and 15 meltdown. Oh, I see. That is what I saw in the chart then. I always, as I've said, I don't follow the markets on a, even not on a monthly basis. I mean, maybe, okay, but there was the spike in 2016 or the drop I couldn't explain. Okay, so it's the meltdown. And the Greek. Ah, it was the Brexit 2016. Why didn't anyone tell me? Brexit, of course. VSTOXX can improve the efficient frontier and offer a cost-efficient way to implement a tail risk hedge. In a volatile equity market environment, tracking error and rebalancing costs increase in equity portfolios. Equity fund managers can go long volatility with VSTOXX derivatives to protect against increases in portfolio tracking error and rebalancing costs of passively indexed. Similarly, convertible bond arbitrage managers can use derivatives to hedge their embedded vol exposure. Trading opportunities. Vol is an asset class, is a growing market and strategy with sustained, and it has a term structure. As the term structure is because options have different maturities. As traders, investors look for new opportunities. VSTOXX derivatives offer a transparent order book and sustained liquidity necessary to trade spreads between European and non-European implied volatility. We got correlations here. VSTOXX minus 70% with the Euro stocks, minus with the US. Oh, it's a pity, right? They don't give the correlation of the VSTOXX and the VIX. The VIX is the S&P 500 option vol, and that's the Euro stocks vol. That's a pity. It should be at least plus 75%. And then that seems to be for the French and here for the British. You know, make a PCA and ask yourself, do I need more than, I mean, I see it's a single index model for sure. Most likely, maybe the VSTOXX is the single index. If not, it's PC1 of these things. And then you have the idiosyncratic part. That's the same logic we used for equity. And people are not doing that in research yet. Very limited because they only a few have the data and then it gets messy, right? Here, VSTOXX VIX index spread. Okay, here they have it. Yeah. What's the time? Financial crisis here, 08. VIX, so the VIX is larger if it's negative. Yeah, that's the US problem here. And S&P cuts Greek debt to junk, yeah, then the VSTOXX goes up relative to the VIX. Or for me, that's like the second principal component, the European PC. If I get rid of the VIX, which would be my first PC. And then here we have Brexit and so on and so forth. Yeah. And then you can buy futures on VSTOXX. If you buy a futures on VSTOXX, you basically you agree today on, you are fixing a price today for the VSTOXX, and you are hoping that within maturity of the futures contract, if you are long the futures, that the realized vol is larger than what you fixed. So you're betting on the spread of the current VSTOXX and the future VSTOXX. And that's why to the question, how can you hedge vol shocks? The most straightforward is to use the futures on the VSTOXX if it's for European. Now, if you want to hedge the vol of BMW or let's say Adidas, let's say Volkswagen, as we have Volkswagen here, right? There's not a VSTOXX traded on Volkswagen. I don't think so. And if so, it's It's just, no, it's not. I mean, maybe it is, but it's highly illiquid. Then one can start to think about how can I proxy for that using the single index logic. For example, if you know that the Adidas option vol has a 0.8 beta on the index vol, then you could use 0.8 of the index futures to hedge the Adidas vol, right? This type of thinking. Again, that's why you see that the index model then makes sense. It's not a perfect hedge because you have the epsilon, the idiosyncratic moves. But at least it's part of a hedge. Okay, these are options daily volume. That's also what we see in our database, that volumes are pretty low. It gets better. What's the black line? These are different expiries. It's the open, no, that's the open interest. Okay, but you see kind of, that's why I also want to teach that in data science. I think like my thinking is that in a couple of years, people trade options the way they trade today equity. And there's so much alpha in options because there's so little research in that. And there is so much, I mean, it's just an exciting field. I also show you that we have an exercise. I show you that if the index moves by 2%, the option moved by 100%. And that within the Black-Scholes world, which for me is a lower bound. So it's just enormous potential. Okay, it's too exciting. I have to stop. Okay, great. So empirical research finds vol shocks are not a linear function of shocks to the underlying. GARCH model assumes vol innovations are functions of the underlying shocks. SVM allows the second moment shocks to be independent of the first moment shocks. It's beneficial for explaining returns on the options and on the underlying. And that's what you want. If you want a trading strategy, like you see how Eurex talks about, yeah, you take an index position, you also take a futures position, and then the options position. I mean, you really want to understand equity, futures, and options at the same time. And we now had a master thesis which ended in collaboration with Eurex. They asked us to build a stress test for Eurex and etc. products, and we just made a bigger thing. We built a risk tool on a daily basis for all etc. and Eurex products, equity and futures, futures on equity, futures on interest rates, futures on bonds, and options on all of these futures, and also options on vol. And the way we modeled that, the Eurex, they didn't know it. They were very excited. We used, like we do in this financial data science course, we used PCAs, we used the idea of single factor models, but we had multi-factor models. Because Eurex came and said, can you use a machine learning approach to get a low dimensional representation of risks in our products, trading risks? For example, you could use lasso regressions and rich regressions. You know, they gave me all these type of words. But at the end, what we ended up doing was we started with finance domain knowledge and then add complexities as they are necessary. Yeah, and I think we have a better model than they have, but we're still in discussion with them right now. Because the way we do it, we have all arbitrage relationships embedded. And the way it's just this PC thing, the way we do it. And that's a big data project. So the student who did it, he's now doing a PhD. He was a Wirtschaftsingenieur. He says for himself, he's 50% informatic, 50% finance. And I think was the right project for him, as the data is just vast. It's just huge. Right. What was a good project? We just had presentation on Friday, so and they won't follow up discussions. We just pitched it to them, and at the end they said they do something similar, but then I said, okay, and then he smiled and said, okay, they want more discussion. Because we made an interim presentation once, and they didn't think in terms of the PCAs, right? They thought about, and also the way they gave me the questions on Friday, I understood. They really think about one asset class at a time: fixed income, equity, option on fixed income. And we kind of take it broader, but with the PC, we are always able, if they come and say, okay, assume there is an equity, there's a DAX crash by 10%, and the V stocks goes up by 30%, and the German interest rates go down by 5%. We're always able then to translate that back through this eigenvalue decomposition back into how the PCs are affected by these industry shocks. So it's very clever. It's very clever. And for example, we learned from a data perspective, equity PCs have a zero correlation with option vol PCs. Right? We just take equity PCs from the etc., like Siemens, whatever they have, and it has nothing to do with the option PCs. To my question, can I hedge options with the underlying? In the theory class, you can, but in reality, you cannot. But interestingly, 10% of equity option vol variations are driven by variations in interest rates. Very interesting. Not understood where that, it's this data science thing. We just found it for now. It was not our objective. We just looked a bit and so on and so forth. But it's interesting. It's interesting potentially. Okay. But as I said, interest rates and volatility, they share a little bit of stuff. So I'm sorry, I get too deep in the topic. I know it's too fast, blah blah blah. But it's just background knowledge, just for people who care. For the others, I think you had a toilet break. So we have 15 more minutes. Let me see what we do. Oh, great. Let me do some data work. Okay. So, again, in the past year, we now spent 2 or 3 weeks on the Kalman filter. Students had to implement that. So you can imagine that's what you heard most likely about the workload in the course. We stripped it down. This time is much more pleasant. We go a different route. For now, we go the package route. And I want you to understand. And not so much implement. Because I learned also in the past, people who can implement, they already can implement. People who can't, you have to do some extra work if you want to learn it. That's why we have these problem sets. Now, what I did, I just was excited. So I just Googled, Python Stochastic Volatility Model. I wanted to see whether I can use a package. Because for the first half of the course, I didn't want to use extra coding. Okay, you see, and then I found something. Stochastic Volatility Model, Python, Harvey transform. That's the estimation approach I cared about. Here, you see, and I found a page of someone who in 2018 made a package. Meaning prior to 2018, there was no such package to the previous students of us to explain why we had to code that in the past. There was no such package. Now there is a guy, he has a PhD, and he then started to work at the Federal Reserve, and he was friendly enough to make not a full package. I just call it like a wrapper package. So he uses a wrapper package that then relies on Python code to do the estimation. And I wanted to use his package. And that's what I do. Again, because we're in the data part, just get to know how to use Python to estimate and to learn a little bit on the way. What he explains here is basically I made a new helper function which copy paste what the guy did. Yeah? It's a helper, SVM, it's the Harvey estimation approach. We just do it for now, and later we will learn about the Kalman filter. First we do, then we learn how. So for this short introduction, I follow Chad Fulton. Yeah, that's the full credit to this person. He rewrites the model slightly differently, but again, it's his package. So you either take his notation or you don't, but it's a good notation. It's just slightly different from mine, but it's fine. You just see YT equals volatility times epsilon. Epsilon is Gauss, and the HT has a drift. I didn't have a drift. And then he always subtracts AT minus mu. So it's always D means here. But otherwise, it's just the same. Yeah, if you think in my notation, I had a sigma upper bar. So just do it at home slowly. Yeah, you can see if you go through the concept here, my notation, it's a little bit different, but you can rewrite one against the other. So we can do it. Maybe we do that. But for now, there's just a package. It explains how it's done. I don't want to go into that for now because I need a full class for that. But you just see he offers on his page such a wrapper model where he relies on the stats models, state space, which is already existent in Python, but gives a little wrapper around it that allows us to estimate the USV model. And I just want to use it. Okay, it's just using it for now and learning about the data implication. So I just do it. So someone has the mic on. Is there a question? Oh, I think you are calling someone else. Right. I apologize. I just muted you. If it's an accident, let me know. Otherwise, I think I did you a favor. Okay, great. So here's what we do. We want to fit the SVM to demeaned market returns. Again, why demeaned? Because it just works for demeaned returns. It's a second moment model, but not a problem, right? We just take the market return and we subtract the mean. That's not a big deal. So we create the SVM object using this helper class. The warning, it's all right. It's just about the date index. I don't care. SVM.fit. Yeah, if we go to the helper function, okay, no. I just do it because I want to compare the SVM volume. So there's a way you can fit that thing, yeah, svm.fit. And I just do it. You see, it takes longer than the GARCH. Did you see? It looked like 5 times longer because there's a fitting procedure involved, the Kalman filter. It's more time intense, but still it's really fast in the package. And let me give me the summary. It's the market return SVM model. And they give me now the parameters of phi sigma square eta mu. They go to the package, phi sigma square mu. Yeah, all the parameters are estimated. I highlight, if you use a package from someone, make sure you follow their notation. Like in the chat, mu was expected return, but it was another exercise. right? Now we are in that exercise. We use his package. For him, mu is the drift in vol. Okay. So that is estimated. So mu, phi, let's go back. What is phi? Phi is the autocorrelation in the variance. Right? Variance is very persistent, 9.8. It's like interest rates, extremely persistent, which makes it easy to forecast volatility. But vol is unobserved. There's always a challenge somewhere. So that is vol of vol. Yeah, if you want. Why vol of vol? Because sigma is vol, and sigma is driven by a shock which has its own vol. And that is called vol of vol. Okay, so we have a vol of vol, and then there is a negative mu here. T statistics, highly significant. Yeah, highly significant. Okay. Now let's just get the conditional vol of the SVM package. I think I do it till 11:30, if you don't mind, but you can always go. I mean, we are close to be done. I would like to finish that thing up. The way I do it, I look at the parameterization at chat. He says volatility is E to the HT divided by 2. Okay, so that's what I do. I say E to the, give me the HT. In the package, it's not called HT. It's called smooth state 0. We will have a full day on the Kalman filter methodology. Then you know why that is a smooth state. We divide by 2 as the model wants us to do. Okay, great. Now we have SVM conditional vol of the equal weight portfolio. And now we want to compare that with the GARCH implied vol. That is what it looks like. Yeah. So if someone shows you a graph and says that is market vol, you should always ask immediately, how did you measure that? Because it's not observed. 2 standard approaches, which couldn't be more standard. And they're different at times. I mean, they're always different. Look at that. Huh? It's a bit like the SVM is a lower bound. Yeah. And then you see these huge spikes. Okay, now we know that is Brexit. I mean, Brexit increases the GARCH vol to 50%. The SVM says no. That is just a return shock, Brexit. But volatility, it also went up, but only to 30%. These are huge differences, right? If you're really trading on such stuff, it's huge. Or look at the COVID, and that's the market. Market vol for the COVID GARCH is 60, 80, goes in 20 steps. So it's like 95%. SVM says, no, it's like 45%. Or right now, last week. Again, COVID, second lockdown, I believe. It said vol is at 50% if you use a GARCH. SVM says, no, we are just at the average at around 25%. Huge differences. Yeah, European crisis, very much the same. Yeah. So if we take the correlation of these two guys, we see they share an 87% correlation. Again, let's go back. What did we do? We fitted a parametric model. Why is the correlation so high? Well, the GARCH has this beta coefficient, which is autocorrelation on the sigma, and it's a bit similar to the phi in the SVM. So we use the same measurements, just returns. The supervisor is the same. It's an indirect supervisor. And the models are different, but not completely different. They are these autocorrelation models, but the SVM allows for individual shocks. But we already know from the GARCH, the arch component was rather small and the GARCH was rather large. So that for me is the reason why these different models give similar results. And I think that you have to do. And I saw in seminars when people came with machine learning stuff, they were not doing that sufficiently, in my view. Because you need to try to make a black box be a white box as much as you can. That is very important. And parametric models help us to learn that, because the models are simple enough for us to look through what's going on here. Okay. Let me just move on a little bit. Awesome question. What do they use to calculate the VIX when there's such a large difference? I mentioned it 5 times, but again, it's complicated. So keep coming with these questions. For VIX, they use option prices. It's a very different animal. It's completely different. And that's why I want to move then towards that. It's like a mystery. For the VIX, they will just use today's options on the S&P 500. Today's option. And that's how they get the VIX. They don't need yesterday's information. They don't need a parametric model like GARCH or SVM. It comes next week, hopefully. So you see, it becomes really exciting. I mean, I can't see your faces and your voices. Most likely you're bored, but I think that is really good stuff. Okay, now let's fit the model to Volkswagen. Once we have a package, just use the package for everything you like. I like just Volkswagen because the short squeeze, it just fools everyone. So let's just see what the SVM makes out of it. Let's fit it. Let's get the conditional vol. Give me the correlation. That is the correlation between the stochastic vol model of Volkswagen and the GARCH. It's just 60%. All right, and look at that. Now, it makes me so emotional when I look at that here. It's just unbelievable. I also saw that the first time when I've prepared for class. When I do the GARCH, I just do it for macro variables or for interest rates, never for something like a short squeeze. That's like a pandemic for the virologen. It happened, it had a fundamental reason. And look how it, in my view, fools the GARCH. But again, how do I know? I don't know. It's just, we have further to investigate, look at options and so on and so forth. But the short squeeze for me, and that's what I have in my notes here, the short squeeze for me is a return shock. The short sellers suddenly had to pay extremely high price in a very short amount of time to cover the shorts. I don't think that ex ante vol was high, but it doesn't matter what I think, right? And you just see, I mean, SVM says, yeah, vol was high, but like it was in 2003, it's interesting to get to know if one wanted to. If someone trades cars, what happened here in 2003? That vol was at 80% for Volkswagen. And they are the same, right? GARCH and so on and so forth. But then the jump here to 500% GARCH, SVM says 80%. It's still large 80% vol. But I mean, 500% it looks ridiculous. But again, let's first wait for the options and further analysis to make our final judgment. Or here Brexit, yeah, most likely. Or maybe it's a diesel scandal, I don't know. SVM goes up, but here again, you see this return innovation squared, which I don't like, yeah? I don't like it because it's parametric, it's kind of forced in course, it could be set to 0, the parameter, but there are also non-jump movements where the algorithm has evidence to put it to non-zero. So, and then the COVID here also, yeah, COVID jumps up to 110%, it looks. SVM is at 50%, huge differences. For example, with the Eurex, why was the Eurex approaching me? Because they do also have an extra firm which does the clearing for over-the-counter trades. Meaning, if you work for a hedge fund and I work for a hedge fund and we trade with each other, volatility, skewness, kurtosis, whatever, then I don't trust you. You don't trust me. We need someone in between who checks. And we could go to another hedge fund, but we don't trust the hedge fund. So the Eurex is offering such a service as well. And the Eurex then, it's Eurex Clearing, another firm, and they want that we post margins, which is collateral, which is money, or something they can liquidate fast, which is like money, like bonds, such that if you default, Eurex is going to pay me what you are supposed to pay me. So the Eurex gets a cushion, take a cushion, and then they get a fee. And okay. And therefore they want a risk tool, which is really good because it's real life, and which is interpretable for all the machine learning guys who are still out there, you know. They want interpretation because the CEOs and the decision makers of the Eurex clearing, they don't want that. Say at the end of the day, I have this neural network, it's a black box, but it works because I have cross validation, and what do I know, right? They said that's not good enough. They want interpretability. And that's why I meant what we did is really smart. I think we can do even better, but it was just one little project. Because the manager of the Eurex can define a project in terms of business talk, like the VIX, the V stocks, interest rates, and then we translate it back into our factor thing and then do our modeling. So they will even not know if they don't have to. But we still talk to them in terms of what is the crash scenario you have in mind. You want to see how the portfolio changes moving forward. Right? And that's such a thing here. If you're in that period and you have a GARCH vol, then simply my simple naive thinking, vol is twice as high. So the margin, the collateral I would have to pay would be twice as high, very simplistically speaking. But if the true vol is the orange one, then I'm just overpaying. And then maybe there's the exchange in London or in Amsterdam who says, I also do clearing for you, hedge fund. And my margins are lower, right? And then we just do the trading over there. And I can just say, I should do this off record, but if you like data science and you are not the guy who's building a car and building the robots, I think this Eurex thing is an extremely lucrative job. It's the highest paid in Germany. Just the median salary, no, the mean salary is 130,000. It's next to SAP. I think they're at 128,000. It's just the mean. And because I know some people there, they also tell me that they have a lot of, okay, I just quote. He said, when it comes to coding, we just have the best we can have. And I mean, go there. If you go there, you see many people from India and so on and so forth. It's very international. He said, what we lack are people who have a bridge position, who can do finance data work, but who can also talk and do some of the coding. And that is very rare. When I think about my PhD students, it's extremely rare. It's extremely rare. And that's why I have this motivation to move this finance data science course and whatever comes in the future into this direction, Because I think you have to do a BWL module anyway. Data science is also nice to do. But in addition, I think you get alpha here. Because these guys try to recruit something that doesn't exist. Because who teaches that? Right? Data science is taught, that will be taught, so on and so forth. That's good. That's really good. But you always need people with finance domain knowledge to really think about it makes sense or not, ex ante, and so forth. Right. And it's a job in Frankfurt for some people who don't want to go international. And I think it's highly, highly paid. And I know one person, he just did a PhD. He worked 1 year for McKinsey. And then they opened a new department at Eurex for like analytics related to this stuff. And then he had 10 people behind that he was supervising. They all had like, they didn't have a PhD. They were like computer scientists most of the time. So it's exciting. I think really that is, and especially given we have the data, there is so much practice one can have just in advance. And then there's no one that competes with you in that area. I think it's a good hedge for the own stuff you want to do. I want to mention that. It's exciting. Okay, now let me just finish up the observations and the implications. GARCH versus SVM. There's model uncertainty clearly visible, right? Each vol time series that we looked at is correct if the underlying model is correct and if we ignore estimation error. Okay, so we have 5,000 observations, so we can ignore kind of estimation error. But the problem is we don't know the true model. It came to me as a surprise, so to you it should also be a surprise that these two standard models give such big differences. It's just, that's a big thing. That's a big thing. So there are stark differences, even for the market, which means the COVID has this 80% vol. Okay, I think I mentioned all of that. I also mentioned that GARCH vol is nearly always larger than SVM vol. I find that interesting. I checked unconditionally, the average is the same, I believe. I think I checked once, although it's hard to believe. Because the orange line is always below, it seems. Here, the prof's view. Yeah, that's my personal view. As I said, I think the short squeeze was a return shock, not a vol shock. The picture suggests to me that the SVM is preferred to the GARCH. In short, I see only disadvantages to connect the ex-ante variance to a current price shock. Noise in price shocks translates into noise in variance estimates. Think about the data error we found in SRP, which means we had these 20 standard deviation shocks in October. We have the data. If you want, just play around. Fit SVM and GARCH to the corrected and the non-corrected return data of SRP. And look at the volatility that comes out in October 2001. I could imagine SVM maybe doesn't respond. Why? Because SVM says variance moves in a diffusive way with a high autocorrelation. So that immediate jump up and then jump down, that would be measurement error, or that would be noise. But the GARCH would take 10% of that roughly into his vol estimate. So that would go whack. Interesting. We will look. I hope we have options on S&P, on SRP. Okay, and now we're getting to the end. SVM, we can make a variance forecast for next period. Because SVM is a parametric model, we can now iterate that forward. So let's use the notation from the package. Although now we use, yeah, that's the package, the helper package. The variance of y, and that's stuff you have. If you don't see that, you have to practice. Let me know. I can give you exercises maybe, but that's just standard math. That's not much. The variance of yt conditional on t minus 1. Yeah, that's what's the variance of the return next period? Okay, what is the variance? It's just the squared y. Why is that? Because the y is demeaned in that specification. It's the d-mean return. Second moment is variance. Now you plug in what's the second moment according to the Chet-Fulton notation. Yeah, it's e to the ht half. Okay, and then you just see what's the expectation of the exponential of a Gauss. That's a trick you should make a red box around. It's just one trick, but it comes over and over again. It's the expectation, it's the exponential of the expectation of h plus half the variance. It's the same trick, right? If you just Google expectation of exponential Gaussian. Yeah, here, right? Just check that yourself. It's a very straightforward known formula. Here's the result. E to the drift plus half the variance. And okay, so that is what I'm doing here. E to the drift, Chet-Fulton notation plus half the variance, right? So therefore, if I take my last ht filtered variable, I just multiply with all the coefficients and I have my estimate for the next period. Okay. Is the SVM Gaussian? No, it's not. Same problem. We have skewness and we have kurtosis. But look, if you use SVM, the skew on average is only 20% of the skew that comes from the GARCH. So the jump potential to the right is only 20% as weird. That's a big, big number because we take the average. I don't have to code here. You can do it yourself. Just take the stats.mean, stats.skew.mean. The skew is 4, and I think it was 17. It was 17 for the GARCH, and it was 600 for the kurtosis, and now it's 26. No. 26, 600 was for the squared returns. Did I compute that for the GARCH? I didn't. Okay, but you can do it. But the takeaways are correct. 26, half the kurtosis of the GARCH, which means if you have a GARCH, you have more excess kurtosis, you need more vol of vol, and you need more upward jumps. And I believe that it's just because you have these return shocks as part of the GARCH, which I wouldn't do it, but I think we should look at the options. Right. That's just stuff it's good to know, right? Because that's very universal. You have a different time series, these takeaways will be the same, just the magnitudes will be different. Okay, I got some comments from the literature. That's really the last 2 minutes. I don't think these are not the big papers. I just Googled a little bit and I found some, even there's a master thesis from a university in Prague, but I thought it might be useful to you who is now asking herself, what do I do with so many vol estimates? Which one do I use? And these are researchers who are paid, academics, who are just having the same questions. You see from the years a little bit, some of them are dated, like GARCH versus SVM was researched in 2002. I meant options started to really be analyzed after 2002, more like 2010. So therefore you see this entire option stuff is not yet incorporated here. But let's just go a little bit. They had a paper choosing the best vol model. And I just give a citation for you for the punchline. The literature on vol models of asset returns has proposed a large number of specifications, starting with the arch model of Engel. So you see it was published in 82, which means even Engel, he worked on that in 75, because we have a lag, publication lag. That's from the 70s. And the GARCH of Boleslav. This gives practitioners a wide range of models to choose from, and naturally leads to the question, which is the best volatility model? It's difficult to answer the question because asset returns often do not contain sufficient information to identify a single vol as best. And that is what I meant when I said asset returns are an indirect supervisor. I want to highlight that because when I saw students last years in our seminars, I always felt they don't think deep enough whether the supervisor they learn is a good supervisor. And if you never get taught that way, of course, you don't know it. That's why I want to teach it that way. If you don't see why asset returns are not containing sufficient information about vol and you've been following this class, then let me know. That's a first order thing. 100% of students should see that. Short answer was that is second moment information, the vol, but your asset returns are more like first moment observations. First moment plus noise. That is very indirect. That doesn't work well. If we observed the true vol, then we had a very direct measure, but it wouldn't be the asset return, it would be asset vol, but it's just not observed. The problem. So value at risk was the paper called GARCH versus SVM empirical study. It was a master thesis. I hope he did good work, or she. I just quickly looked. I thought the abstract is useful for you. The thesis compares GARCH vol models and stochastic vol models with a student T distributed error. Okay, so he doesn't take a Gauss shock, he takes a student T shock. Okay. And it's empirical forecasting performance of value at risk. I'm not sure I mentioned that last week, but how do I know that's a good variance forecast? That's why I post these abstracts from the papers. So you learn what the researchers did. They look for a quantity like the value at risk, because if you have a vol forecast, you can translate that into the value at risk, and then you can check whether the value at risk was breached too often or too little in the data relative to the model. Again, it's very indirect, and it needs a lot of data. Because the value at risk is a low probability event. So it should only happen if you have the 95% value at risk, it should, in 5% of cases, you should have a loss, which means 95% of your data you throw away, basically, for that test. So it's very inefficient, but yeah, one thinks it's the best way one can do. Okay, it introduces in details the problem of SV models, maximum likelihood estimations. Exactly, as I said, we cannot estimate that with SV. We have to use the Kalman filter and suggest the newly developed approach. Okay, he uses a Bayesian approach. I will teach you a simpler one. Okay. Right, again here, they use a comparison. They have an in sample where they train the model and an out of sample where they check whether the value at risk was over or underestimating the losses that came in. Yeah? Okay, we show that SV models can perform at least as good as GARCH, if not superior. Okay, that goes into there's a selection bias maybe in the paper, because I have the same thinking that SV, all else equal, I would trust it more, and I hope it's clear why, given today's presentation. Okay, and this last one, Leha, GARCH versus stochastic vol, option pricing and risk management. Okay, interesting. Talk about option pricing. I just copied the conclusion from the paper. In this paper, the performance of 3 option pricing models is evaluated. We compare the Black-Scholes model And we talk about that in 2 or 3 classes. 2 valuation models using GARCH and SV. The 3 approaches are calibrated to intraday market prices of FTSE 100 contracts. The performance is evaluated by means of pricing errors and by the fit of a VAR application. So you see, again, they use value at risk like above, but it's more scientific. The other one was a master thesis that these are researchers who do it for a living. So they do also option. Our first conclusion concerns the behavior of pricing errors. We document that GARCH dominates stochastic vol and the benchmark Black-Scholes model. That's in terms of option pricing. Okay. It achieves significant overall improvements in pricing performance. The pricing difference between stochastic vol and constant vol are small. We thus observe that the choice of vol model is crucial for the pricing of options. However, these differences in performance are not apparent in the context of risk management. That's kind of awkward, isn't it? To examine the competing methodologies in the context, we use the value at risk framework. Monte Carlo simulation with full valuation provides the forecasts of the expected profit and loss over a given horizon. As our second main conclusion, we find no measurable difference between value at risk forecasts of the 3 models. Again, what I say, it's very inefficient, this value at risk thing, because you go for low probability events. That's interesting. It doesn't make a difference in terms of characterizing the tails. But then why does it matter for the options? I wonder. So we will talk about options. So in particular, we document that all 3 approaches exhibit a weak fit to the realized profit and loss. Weak, yeah, so they don't have a good fit. So they underestimate risks, it seems. Overall, we conclude that the performance of the model depends on the loss function you apply. Goes back to the question above about what is the best vol model. It first depends, that's a takeaway. What are you trying to achieve? It's the loss function that matters. Okay. The GARCH model fails to forecast the tails of the distribution of option returns. That's interesting. But keep this in mind. I think because I looked a bit into our option set, something similar comes out of that. We discuss the divergence and conclude the assumption of normality is problematic. Okay, so takeaway. Yeah, you just think about it, and I will post a problem set, and it will be on the SVM most likely and the factor model, and maybe compared to the GARCH factor model or something like that. Okay, great. If there are issues, let me know, right? Now we come to the part of the course where it becomes even more delicate, because we have to talk a little bit about option pricing, about valuation, so on and so forth. The more I know about your weaknesses and interests, the better I can tailor, I think, the presentation for you. Okay, great. Otherwise, was a fun class.